In the previous videos, we looked at solving exponential equations. In this series of videos, we're going to look at solving logarithmic equations. And a logarithmic equation, by definition, is any equation that contains one or more logarithms within it. Now, a process that we can use to solve this is to, first of all, try to use some of the basic properties of the log equations to try to get to a single log if necessary. If it's not basic, we want to try to get all the logs to one side and we want all the real numbers to the other side of the equation, if at all possible. Then we're going to use our rules to where we can change a logarithm into an exponent. And we remember the mantra that a logarithm is an exponent. So we can use the base and the exponent to be able to transform that function. Then what we're going to do is we're going to raise both sides to the power of the log base, and then finally we are going to solve the remaining equation and check for any extraneous roots. Because remember, there's domain restrictions. Okay, so we have to be cognizant that if we have a log base b of x, we have to recall that x has to be greater than 0. All right, so given all of this, let's go ahead and solve a few basic sorts of logarithmic equations, and then what we can do is work our way up to a little bit more difficult ones as we go along. All right, so first of all, we have this log base 2 of 3x minus 1 equals 5. All right, so first thing we're going to do is let's translate this into an exponential equation. So remember, a logarithm is an exponent. So this is the exponent, this is the base, and so we're going to rewrite this as 3x minus 1 equals 2 to the 5th power. We know 2 to the 5th is 32, and we could either use our calculators or we could just multiply it out. And then we could just solve this by adding 1 to both sides, and that gives us that 3x is going to be equal to 33. And then finally, we divide by 3, and our answer that we get is x equals 11. Now, the last thing we should do with logarithms, and we haven't done this with exponential equations because exponential equations, the domain's all real numbers, is we should check the answer. Okay, so we're going to substitute 11 back in just to make sure that there's no violation of the domain. And so when we check this, we have log base 2 of 3 times 11 minus 1 equals 5. And really what we're looking for was just making sure that whatever's inside the log is greater than 0. We know 3x minus, or 3 times 11 minus 1 is 32, which is greater than 0. So that's good because there is no domain restriction. All right, so that one looks like it's going to be our solution for us. Another example, another fairly easy example, 2 log base 3 of 2x plus 3 plus 1 is going to be equal to 5. So first thing we want to do, isolate the log term. So we are going to subtract 1 from both sides. So we get 2 log base 3 of 2x plus 3 is going to be equal to 4. Then we're going to divide by 2, because that's the coefficient for the logarithm. And so we get log base 3 of 2x plus 3 is going to be equal to 2. Now we're going to use that trick. Okay, so we have our exponent is 2 and our base is 3. And we're going to just say that now 2x plus 3 is going to be equal to 3 squared. When we evaluate that, that just becomes 9. We're going to subtract 3 from both sides. Right? So we end up with 2x is going to be equal to 6. And then finally, we divide by 2. And so we end up with x is going to be equal to 3. We're going to check our answer by substituting back in right here inside. We just need to make sure that that expression is greater than 0. Okay, so when we check, we're just going to have 2 times 3 plus 3, and that's going to give us 9, which is clearly greater than 0. All right, so that means that x equals 3 is part of our solution set. All right, another example really quickly is the log example, or the natural log. And so we have 3 ln of 2x is going to be equal to 12. So let's start by isolating the ln term. So we're going to divide both sides by 3. And so we're going to have natural log of 2x is going to be equal to 12 over 3 is 4. And then you probably remember that e's and ln's are inverses of one another. And so we're going to say e to the ln of 2x equals e to the 4th. And then there's that rule that at this point we could just make that e ln of 2x just into 2x equals e to the fourth. And the last thing we're going to do is divide by 4, or sorry, divide by 2. So x is going to be equal to e to the fourth divided by 2. All right. It doesn't, as long as the number here, and clearly any number that we plug in to 2x, as long as that number is bigger than 0, that's going to be in the domain. Okay, so this one's clearly in the domain of the function. Just a couple more really quickly, because these are easier ones. We have this natural log of square root 8 at minus x equals 5. And so one of the rules that we remember is if we have a square root, we can write that as a 1/2 power. So that's going to be x minus 8 to the 1/2, which is equal to 5. And then another rule of logarithms that we remember is that we can move the 1/2 in front if it's an exponent. So we can write this as 1/2 natural log of 8 minus x equals 5. And then we can multiply both sides by 2 to be able to clear out the 1/2 power. So I'm going to multiply by 2 over here and 2 over here. And that's going to cancel these 2's out. And so we get ln of 8x minus 8. Excuse me. So this will be ln x minus 8 is going to be equal to 10. We raise both sides to the e power. And that e's and ln's undo each other. So we're left with x minus 8 is equal to e to the 10th. And finally, we would just add 8 to both sides. We know that e to the 10th and 8 are unlike terms, and so our answer, x is going to be equal to e to the 10th plus 8. Now, if we were to substitute that back in, all right, that would make a lot of sense if we were to go substitute. So just to check this one really quickly, that becomes the natural log of the square root of e to the 10th plus 8 minus 8 equals 5. Those 8's cancel out. We have the ln of root e to the 10th equals 5. We know the square root of e to the 10th is going to be e to the 5th, and then the ln of e, so 5 equals 5. All right, so that is in the domain. All right, and that was just a really quick one to check. One last easier example, log base 6 of 7x plus 4 is equal to log base 6 of 3x minus 15. One of the things that we notice is that they both have a base of 6. And if we have a base of 6 on both sides, what we could technically do is we could just get rid of the log, or we could just raise both, just have base 6 on both sides. So we would have 6 log base 6 of 7x plus 4 is going to be equal to 6 raised to the log base 6 of 3x minus 15. All right. Now, what you could have done is just at the beginning of the problem, cancel out the log base 6 because they're the same on both sides. But technically, this is what's going on behind the scenes there. Okay, if we raise both sides to the 6th power. Okay, so, or have a base of 6 on both sides. So we would have 7x plus 4, because these log base 6's would all cancel out, is going to be equal to 3x minus 15. Now we just have a basic linear equation. We're going to subtract 3x from both sides. Right? So if I subtract 3x from both sides, that's going to give me 4x plus 4 equals negative 15. And then I'm going to subtract 4 from both sides. And that's going to give me 4x equals negative 19. And we divide both sides by 4. So our proposed answer is going to be x equals negative 19/4. All right, now that looks like it might be a bad answer, okay, because obviously we can't have a negative in the logarithm. But just because a number is negative doesn't necessarily mean it's not going to be a solution to the logarithm as long as it doesn't make what's inside negative. All right, so the last thing we're going to do is we're just going to go in here and we're going to check to make sure that neither of those values make it anything less than negative or less than 0. Okay, so on our check, let's just substitute our answer into 7x plus 4. That's going to be 7 parentheses negative 19/4 plus 4. And what we could do is we could just throw that right into a calculator really quickly. All right, and this has to be greater than 0. All right, so this thing would have to be greater than 0 for this to work. So we're going to go into our scientific calculator, and we could just say, let me clear this mess out. 7 parentheses, negative 19/4, and then we had plus 4, I believe. All right. Now, that gives us negative 29.25. All right. As long as I type that in correctly. So that has to be negative 29.25, but that is not greater than 0. All right. So unfortunately, what that means is that this is not part of the solution set. So this is not part of the solution set. All right. And that means that the answer is actually going to be a no solution. Okay, or 0 with a slash through it. Okay, so not every logarithmic equation does have a solution. Okay, sometimes they're outside the bounds, and unfortunately, when that happens, then we get a no solution. So this is just an introduction to some of the easier types of logarithm problems. Now, in the next series of videos, we're going to take a look at a few more of them that are a little bit tougher, that have to use some of those rules of logarithms before we go through and actually solve them.